Hello guys! So I was analyzing an article titled Supervised Multimodal Bitransformers for classifying images and text, which is not a very famous or well-known article like other models such as Transformers, BERT, or ResNet. I mentioned these models because they use these models in this article, but as I said, it is not a breakthrough article, although it has 290 citations. I thought it would be a good idea to create a video after reading and analyzing this article, since there is no video about this article on YouTube, and I'm doing this in English. Since English is a common language, it might help more people to understand this article. Also, before I start, I want to mention that by no means I'm a professional. In fact, I'm really new to this field of AI, so I might have some mistakes here and there. So I tried my best to read, research, analyze, understand, and then explain this stuff to you. So let's start, but before starting, let me connect to my tablet so I have the ability to draw, and it's a little blurry here, but I try to zoom in so you see stuff. As I mentioned, we are analyzing supervised multimodal bitransformers for classifying images and text. And I have some notes here and there. When I analyzing things, the things that I don't know, I do research about them and take some small notes about them. You might see these notes a lot throughout this article. And I wrote the goal is to predict a single classification label or multi. I'm gonna correct here myself because we can have multi-label classification. Okay. In overall, the abstract and the introduction part from here to here. So as we know, modern data and the internet isn't just text, it's often a mix of text and images. While models like BERT have revolutionized how we handle text alone, they don't automatically know what to do when an image joins the party. And in digital environment, data really comes just as text. More often we see a combination like text with images, sounds, or even videos. This means that when we try to classify or analyze data, for example, figuring out the topic of a movie or identifying food in a recipe that we do in this article, we need models that understand more than just words. Here they mentioned, while there have been efforts to extend these ideas to work with multiple types of data like VLBERT, VisualBERT, LXMBERT, or VLBERT, I don't know these models. I didn't read their papers or analyze or search about them, but they mentioned that these models do work with multimodal like images and text together. These models usually involve complicated training routines where the system is pre-trained on large, specifically crafted multimodal tasks before being fine-tuned on a specific job. The authors introduced a supervised multimodal bitransformer. In plain terms, this is a model that uses existing pre-trained models, one that understands text like BERT and one that understands images like ResNet, and bridges the gap between image and text by translating image features into a format that the text model, here the BERT model, can work with. You can think of it as translating image into the language of text tokens. And finally, fine-tune these combined models on a specific task that requires understanding both text and images. They also claim that despite being simpler than more complex models, for instance those that require massive self-supervised pre-training like VLBERT or other models that were mentioned here, the provided method matches or even exceeds the state-of-art accuracy on several multimodal tasks. They also say that this model provides great flexibility and extendability because it relies on pre-training models like BERT and ResNet. If a better text or image model comes along, you can swap it in without needing to redesigning everything from scratch. I want to mention an important note. Their method centers around BERT, meaning the system is built so that everything eventually fits into BERT's token-based framework. This makes the fusion of text and image data more natural and allows the model to leverage BERT's strength and power. The authors test their approach on three specific classification tasks, MMIMBD, Food 101, and VSNLI, that while involving images are heavily driven by the text. By that I mean, in these models we see more text than images, which is common in real-world scenarios where text plays more dominant role. So it was the overview of the abstract and introduction. We come again and take a look at this, but not right now. In section 2, Multimodal Bitransformers, they explain for a long time AI researchers in both text and image fields, they realized that it is useful to first train models on a lot of general data before you're trying to solve a specific problem. This pre-training approach, also called transfer learning, has become a standard way of doing things, but there is no much important stuff at section 2 here. I do have a note here. It's about ImageNet. Okay, that's not an important note. And they have, okay, here also it's not an important thing, but the explaining of the model will start at section 2.1. It's a subsection. In this subsection, the authors explain how they process image before feeding them into the multimodal model. In typical computer vision tasks, a pre-trained convolutional neural network like ResNet 152, which we are using here, usually these networks pull the final feature map into a single vector, which is a summary of the entire image. If you don't know what pulling is, it is basically a downsampling operation that reduces the spatial dimensions, height and width of the images or input feature maps, while retaining important information. To better understand it, think of the image as a big puzzle, and each piece of the puzzle holds some information about the picture. Now, instead of looking at every tiny puzzle piece in detail, you just want to look at some important pieces that give you a sense of what the whole picture is about. So basically, they remove the last pooling layer in the ResNet 152 architecture because the transformer can work with multiple inputs, and this way it works better. I explain it a little more in a moment. Even instead of looking at this, I actually prepared something to visualize and understanding this subsection 2.1 from here 2.1 image encoder, 2.2 multimodal transformer input layer, 2.3 classification, and 2.4 pre-training. I'm not sure about fine-tuning in visualization, but yeah, I actually create something here so you can understand it better. So we have an image and a text. Our image is going to feed into the ResNet 152 model first, extract some information, and feed it into pre-trained BERT along text. And at the end of that, the BERT is going to use a classifier to decide which labels or label the input is belong to. It's a high-level architecture. Let's dive into more, and starting from image. So we have image. We have a pre-processing steps. Before feeding the images into ResNet 152, they resize, center crop, and normalize them to ensure consistency and quality of the feature extracted. So each image is going to be resized to 155 to 255, and then center crop to 224 to 224, and then normalize the values with mean and standard deviation. It is the pre-processing, and I took this picture from the code, which I will link to the GitHub page where they share their code on the description of this video. You can find the code there and run it for yourselves. Instead of reducing the image to one vector, they modifying the pooling steps so that it produces multiple output vectors. So they actually remove the fully connected layer and average pooling at the, by the way, it's not the architecture of the ResNet 151, it's the architecture of the ResNet 50, but I find this, let's think it is that. The architecture is the same actually. We have convolutional layer, then we have pooling, then we have convolutional pooling, and it goes like that. ResNet 152 have more of this, ResNet 50 has less. But as I said, they remove the fully connection layer and fully connected layer and the average pooling from the last one. And so we have here, instead of having one vector summarizing the whole image, we have multiple vectors. Think of it as breaking the image into a grid of k by m cells, into cells, let's say, and extracting a detailed feature vector from each cell. By the way, the vectors that come out of this, each of them are 2048 dimensional. Okay. And if you ask why they do this, having multiple vectors means the transformer can attend to different parts of the image independently, and this granular information is beneficial when combining image data and text, allowing the model to focus on specific visual details relevant to the classification task. So while analyzing the code, I saw that the output would be a 2048 by 7 by 7, and they actually apply an adaptive pooling themselves and a pooling layer themselves, and they call it adaptive pooling because this layer can change according to the parameter that we give to the code when we're running it. For example, I have a screenshot here. According to the parameters, it could be an average pooling or a max pooling, and according to the num image embeds here, according to this parameter which user gives to the program while running it, they actually define the pooling. If, for example, if it is 1 2 3 5 7, it's going to be like this, 7 to 1, for example, if it is 7, or 3 to 1 if it is 3. But if it is 4, it is going to be 2 by 2. And after they give this output, the pooling layer here, we will have a 2048 time n, and this n could be, according to this pooling function, could be one of them, for example 7 1 or 2 2. Then they apply flattening. What is flattening? Flattening refers to the process of converting a multi-dimensional array like 2D image or 3D feature map into a one-dimensional vector. So here, if n is 1 7 1 or 2 2, they are going to convert them to, if it is 2 2, it's going to be 4. If it is 7 1, it's going to be 7. So basically multiplying them and put them in one dimension. And then they apply transpose, which is replacing the position of n and this number, which is 2048. And after that, we can see this here, like in the code, they apply pooling, then flattening, then transposing. And here we have B. If you analyzing the code and you wonder what is B, it means batch. By batch, I mean they do not apply this on one sample at a time. They create a batch and apply to multiple samples at a time, so it be faster. And after that, they have in vectors of the 2048 dimension. Then they feed each of these vectors to the linear layer, which has an input of the 2048 and output of 768. And why is 768? Because it's a vector that BERT can work with it. So as we know, BERT is built to process sequence of tokens like words, which each token is represented by a vector which is a 786 dimensional vector. To use BERT for multimodal data, we need to translate the image features into a format that BERT understands, so that both text and image tokens live in the same space. That's why they actually feed it to the linear layer. And if you don't know about BERT, let me talk shortly about how BERT works. BERT normally takes text tokens and computes an embedding for each token. By token, we could mean just a word. So if we have a sentence, for example, if I have a sentence, we are reading this article. We can divide this sentence into words or subwords or characters, but BERT usually divide them into words, so each word is going to be represented as a token or referenced as a token. And then from each word we are going to extract some embeddings. So by that I mean convert the text into a number which is a representation of that text. And we have token embeddings, which is the basic representation of the word. Then we have positional. Let me show you from here. If we come here, okay. So every word is referenced as a token, and from every word we are going to get a representation. By that I mean an integer that represents that word. And then positional embedding, which encodes the position of the token in the sentence so the BERT model have an understanding where the E is located in the sentence, so it has the order. And then segment embeddings, which helps to distinguish between different segments like sentence A or sentence B, if we have two sentences. But here a segment is used to distinguish from text and images. Now, after we have converted image embeddings in the format that BERT can understand, we create a single sequence for the transformer here. We have image part and text part. By the way, I didn't add the positional and segment embeddings here, but basically what we have is this. Let me show you. Is this. We have image, text, token of image and text, the positional embeddings, the segment embeddings. By the way, in the figure, they illustrated that they put images second, and here we have text, here we have image, but in the code, I saw that for the model, for MMBT model, Multimodal Bitransformers, they put the image first and text second, then add positional embeddings for both. They start from 0 to the number of the words in text and or tokens in text and number of tokens in image, and then segment embeddings 0 for image and 1 for text to actually be able to distinguish between text and image embeddings in the model. I did not understand the code very well, or I could not read it very well, but I'm pretty sure that they reversed the image and text part and put the image at first with the segment position of 0, which I don't know the reason why, but I think from my perspective it should be the same, since BERT is a transformer actually, and they apply all attention, so the all embeddings have effect on other all embeddings, but it should be a reason to actually reverse the positions for just that model. If you analyze this article and understand why they did this, or if I'm wrong, please mention it in the comments. Otherwise, I'm pretty sure that they did what I'm saying here. So after that, as I told you, they concatenate them, put CLS and SEP. These are special BERT tokens. That is, for example, SEP is a separator which is added to each segment at the end of each segment, one for the image and one for the text here, the image here, the text here. And CLS is a special token which I will explain it a little more in a moment. But as I mentioned, both set of tokens from text and projected image embeddings are concatenated into one sequence. This unified sequence is then fed into the bidirectional transformer here, a pre-trained BERT, to allow self-attention across all tokens, meaning the model can learn to relate words and image regions directly. This way, the transformer can directly learn which parts of the text relate to which regions of the image, resulting in a richer, more fine-grained multimodal understanding. After we give this token to the BERT model, the concatenated token. After processing the combined sequence of text and projected image token, the transformer produces a sequence of output embeddings. So here, BERT gives us the output embeddings. The model uses the first output embedding from the final transformer layer as a summary representation of the whole input. This analogous to how BERT uses the CLS token for classification. So here we have output embeddings and we just get the CLS token out here. And CLS token, if you don't know what CLS token, let me explain a little more about it. In BERT, a special token CLS is added to the beginning of each input sequence. This token doesn't represent any actual word from the sentence, but serves as a placeholder that aggregates information from the entire sequence. The main idea is that during processing, the transformer layer uses the self-attention to mix the information from all tokens, which is words, or in our multimodal case, both text and image tokens that we give it to BERT model. The final hidden state corresponding to the CLS token is designed to capture an overall representation of the entire input. For example, when you tokenized your text, let's go back to the examples that we get. Before giving it to BERT, we add CLS token at first and then get a representation from every word. So we have a representation T1 for word 1, T2 for word 2, and goes to Tn, which is here 1, 2, 3, 4, 5, which is T5 for word 5, and we have a separation embedding here. Then we have positional embeddings, which is 0, 1, 2, 3, 4, 5, and here 6. And then segment embedding, because it's just one sentence, we have all 0. And we give it to the BERT. We give the whole combination of this as the input to BERT. And as the input passes through the transformer layers, each token's embedding is updated by attending to all other tokens in the sequence. This means that the CLS token learns from the entire context. By the end of the final transformer layer, the updated CLS token embedding is a context-rich summary of the whole sequence. This is because it has absorbed relevant information from all the other words or tokens via the self-attention mechanism that we saw in transformers. This representation is then fed into a simple linear layer, a fully connected layer that maps it to a vector of scores for each class. So CLS vector is a 768 dimensional vector, and we give it as an input to a linear layer and output as n classes. Of how many classes that we have, it depends on the dataset that we use. And for unique classes, so datasets that have just one class for each input, model applies softmax function on the output and then train using cross entropy loss. Basically, if our dataset contains data that just belongs to one label or to one class, just one of these neurons are going to light up. But if it is more than one, we apply sigmoid function that look at every neuron, and there is a threshold of 0.5 in the code. If it is more than that threshold, then that neuron is going to light up, so the input can belong to two labels. And if you see here, we have some information here. Yeah, they use 3 data sets, and look, this is the first one is multi-label, which is which use poster and text to decide what categories a movie or a poster movie belongs to. For example, a movie can be at the same time a dramatic and comedy, or be action and comedy. So we have multi-label. Multi-class means uni-label, so just one label. And the other information about the data type, for example, how much is it used for train, how much is it used for actually validating, how much is it used for testing, the number of inputs that they have, and number of classes that they have. So if we use the first data set here, at the end, it would be 23 neurons. So we have 23 output. Since it is multi-label, one or more than one of the neurons can be light up. But if it is another one, so if it is food 101, we have 101 classes and only one of the neurons can be true, so only one label can be set to the input. And if we have the other one, VSNLI, then we have 3 neurons at the output, so one of them can be. And so basically I actually explained this part and this part and this part here. So the section 2425, they talk about what models they use, how they fine tuning it. They have methods like freezing the models. For example, PreBERT and ResNet don't need to be updated at the first because they are general models, but after sometimes it's better to actually train them according to specific data sets. They actually give some examples from the data sets and the evaluations, that what models they actually compare their models to, and the results that they got, and what metrics they use to actually compare the results, and other things which everyone can read for themselves and understanding it. For example, here they analyzing the freezing pre-trained text and image components. So basically you can read the rest, but the whole idea of the model in this article was the one that I try to explain here. And it is from my understanding, I actually analyzed the code and article together, and I could have some mistakes in the way, but after days of the reading, analyzing, researching, and trying to understand the code and the article, I got this. So I wanted to share it with others so they can analyze it or understanding the article much easier than me. I hope I explained this article in a way that you could understand. If you like this video, you can share it with someone that might find it interesting, or liking it, leaving a comment if you have questions or suggestion. But that's it. Have a wonderful day or night.